Okay. Hello again. Happy to see you all here in a numerical simulation in metal forming lecture. For this semester, I will present this topic together with Mr. Faisal Qayyum. I think this is the first session for the lecture, and in the first two sessions, Mr. Qayyum talked about a little bit about the simulation and more about reviewing the fundamental concepts in metal forming, which conceptually we need this knowledge for understanding this topic, numerical simulation in metal forming. And okay. Let's start our session today. The content of the session, of course, not only this session, today's session and the next week's session. These are the contents. First, we talk about the finite element modeling, exactly what is this, what is finite element modeling, and then we talk about basic concepts in finite element, like how we can solve the equation, what's discretization, and what's discretization on time, and what's the difference between explicit and implicit FEM. And later, it would be next session talking about adaptive meshing and contact problem, the boundary condition, how we can apply, and finally, a summary on this topic. So, as far as I know, the last session for the lecture was closed with this slide. Is it right? Okay, no feedback. I'm not sure. Can you hear me well or not? Please give me a feedback again. I want to be sure that you can hear me. Okay, okay. So, the lecture was closed with this slide, which is talking about the blocks and the parts we have in a simulator. So as Mr. Qayyum explained to you before, we have pre-processing, which you apply the initial condition in your pre-processing as well as boundary condition. You have to apply the boundary condition. Then your given information goes to solver. Solver is the brain of this simulator. In solver, the equations are solved. Today we will explain a little bit, not too much, about the way that the computer and I mean in FEM we can solve the equations, and then the results goes to post-processors, so you can check the results in post-processor graphically or in any other way. So, okay, before talking about FEM, exactly FEM, first I talk about the simulation. That's what is simulation and why we use the simulation, what are the advantages and sometimes disadvantages of the simulation. Of course, I can say that by itself there is no disadvantages, but sometimes in the point of view of accuracy or the time, sometimes there would be some disadvantages for simulation. Okay, as you can see here in the figure, in the photo is showing the upsetting of a very big block of steel, maybe. So if you compare the size of the block and the size of the operator here, you can see how big is this process and how difficult it is to set such a process, and of course how difficult to set up and to repeat such a process. So in this case, before carrying out the practical case, we have to gather some information about the process, and simulating the process is one of the way we can analyze the process before carrying out. There are different definitions for simulation, as you can see here. The first definition of simulation is the idea of simulation is to reproduce the reality in a model as detailed as possible. And of course, it's important that you can conclude some results from your simulation. Okay, I have marked some points in red because each definition is looking into the matter, into the simulation from different perspective view. But in the first definition, reproducing the reality is important and as detailed as possible. So this as detailed as possible means that you should give as much as possible information to your simulation if you want to make it more accurate. But you should know that if you give more information, if you make it, it means that you are making the simulation more complicated. And complicated simulation means more time to solve the model, and sometimes giving more information in the mathematical form is not easy and sometimes sacrifices the accuracy. And okay, that was the first definition. In the second definition, it's telling that simulation is representation of a system with its dynamic process in an experimental model to reach findings which are transferred into reality. And the third one is defining the simulation in this way, that simulation is the conscious initiating and reproducible initiation of technical system with the help of programs. Yeah, it's consisting on the program. So you use computer or software or program for your simulation, of course. So as you can see here, I can say that this is a simplified model of this upsetting process. Of course, why we say simplified? Because of course you cannot simulate your physical model exactly same to what's happening in the reality. It's not possible at all, because sometimes you cannot consider what is happening in reality by mathematical equation and mathematical model. So computer just understand the mathematics. So if you cannot do state it in the mathematical language, then you cannot use it in simulation. Sometimes you cannot. And sometimes even if you can, it will take much more, a huge time to solve the equations and solve the problem. So we have to simplify. But how we simplify? We can simplify in a way that it does not harm the results in the area we need. Then, yeah, we will talk about it later a little bit more. But for example, here we assume that the material here is continuum. It means that there is no porosity inside, but you know that in reality there is. such a big block of steel, of course, there is segregation inside, there is inhomogeneity, there is porosity, but in simulation, we ignore these small things because that would not be affect the result that much. And of course, we apply the boundary condition. We talk about the boundary condition more and more later. The specimen is in contact with upper die, lower die. You have thermal heat transfer. You have friction here, and also convection. So you can see that you should solve, not you, of course, computer should solve different type of equation for mechanical equilibrium, for heat equilibrium, and so on, to solve the problem and give you some results. However, I can say that finite element or simulation generally can give a good result if you simplify it in a right way and if you calibrate it well with the experiment. Then you can obtain, of course, good results. For example, here in this figure, you can, the left one is the experiment showing the metal flow lines here. Metal flow lines, it's a concept in metal forming. The metal flow line shows that how the material is flowing during the deformation. So, for example, if you have an upsetting sample here like this, and you can make some metal flow lines in this way. Okay, oh, it's not going. Okay, the lines should be straight. Okay, I cannot. It's not easy to. Draw well, and after upsetting and deformation, okay, you know that you have a dead metal zone here, for example, in this way, and here dead metal zone here by the upper and lower die. So if you check the metal flow lines, the metal flow lines here is not changed too much, but here it's like this, and again straight, and also for the second one, like this. So this is metal flow lines, and here the experimental metal flow lines are compared with the predicted one on the right side. And if you look into the figure precisely, you can understand that the simulation is giving almost I can say predicting almost correct flow line compared to the experiment. Okay. So, we talked about the simulation. Now, what is FEM, or finite element method, and why we use FEM? Okay, for simulation, we can use different methods. We have the finite difference method, finite volume methods, which is used usually for the flow simulation, for CFD simulations, and we have finite element method, which is used in our case because our concept is metal forming. We usually use, not usually, but all the time use a finite element method. So what is finite element method? The name shows the meaning. The finite element method is a numerical method for solving the problem of engineering and mathematical physics. But we solve the problem and the equations on a finite part of the material or workpiece. I mean, it's better to say that we break down the material into small pieces and then we solve the equation on each small pieces, and then just gather all the information and represent it in the form of simulation. That's why we call it finite element method, because the equations are solved on finite elements. So typically different kind of process and physical phenomena can be simulated by finite element. Structural analysis, which is this finite element method, started with this and then developed to other branches of science. And heat transfer, fluid flow, of course, it's finite volume, and mass transport and electromagnetic potential, and many other examples you can find for using finite element in the simulation of process. And why finite element? Okay, if we do not use finite element, which method usually we use? Okay, imagine that you cannot use finite element method or software in company. Then which method do you use for your calculation, for your design in company? Anybody knows the answer? Okay, if you do not know the answer, at least send a no, then I would be sure that, okay, everything is going well and we are connected and you are listening to my lecture. Okay, but the answer is written here. Oh, thank you. The answer is written here. We usually, if you do not have a tool like a simulation or FEM, we use the analytical solutions. The analytical solutions, we have used such analytical solutions in different topics, in different, like in physics, in mechanics, in many lectures and many topics you had in bachelor and in master. So if you have an equation, and then you, based on that equation, and you can obtain some values from the equation. But the problem is that you usually have the analytical solution just for simple problems. If the problem becomes complicated, then you cannot develop analytical solution easily. That's the problem. For complicated geometry, complicated loadings, and complicated material properties, of course, you cannot use such a simple analytical solutions. For example, in the case of metal forming, because rolling is a kind of simple process, so later you will see that you have some analytical equations for the rolling or for the extrusion for such a simple processes. But for complicated processes, you cannot. You don't have such analytical solution. Okay, looking to this figure, it's the forging. It's simulating the forging of a flange. Of course, it's just a cross section, and it's asymmetry. So you should rotate it 360 degrees to see how is the real workpiece. However, you can see that the die is very complicated, upper die and lower die, and this figure is predicting the temperature field. You can see that you have heat transfer, and temperature field becomes very complicated here, and the deformation and also the metal flow line. So, of course, you cannot solve such a problem using the analytical solution if you want to have the accurate answer. Yeah, if you want to have a rough estimation and a rough answer, of course, you can use the analytical method. But for the accurate answer, the only way we have at this moment is finite element method. So we need to rely on numerical methods such as finite element method for acceptable solutions. Acceptable here means with acceptable accuracy. Okay, so from the point of mathematical view, finite element method or FEM is one approximation method for a solution for partial differential equations. Okay, so I said that if you want accuracy, we use the FEM, but now you see here that even in FEM, there is we have a kind of approximation. And approximation means some errors comes into the calculation. But if you set your simulation well, if you model it well, and if you run it well, then you can minimize this error and you can obtain much more acceptable result compared to other analytical solutions. Because as I said, in analytical case, you should make the model really simple, which is, I can say that in many cases, it is far from reality. For example, again, in analytical solutions, usually we solve the problems in linear form because solving the nonlinear equations is not easy. But in FEM or any other way of simulation, you can apply nonlinearity. And in real cases, in reality, I can say that most of the phenomena showing the non-linear behavior. Even the phenomena we assume it linear, but in reality they are not linear. So in the case of deformation, for example, we assume that in elastic area, we have a linear relation between the stress and strain by Hooke's law, of course, you know. But in the case of plastic deformation, when you have a massive displacement, then there is no linearity. And sometimes, usually, the material, the solution depends on the material property, and material properties shows a non-linearity. And of course, on the contact and on the boundaries, again, you have many cases of non-linearity for friction and other things. So you can see that FEM, how FEM can help us in solving our problem, especially when the problem contains many non-linearity. Of course, as I said, in many cases, I can say in all physical cases, we have non-linearity in behavior and as well in other aspects. Another opportunity FEM gives is that we can couple the problems. Okay, imagine that you have a hot deformation process. So you have deformation and you have heat transfer together. Okay, if you want to solve such a problem, analytical, it's not easy because you should solve the heat transfer equation. On the other side, you should solve the deformation and mechanical equilibrium equations. So, but with FEM, you can couple these two together. Even more, you can apply the metallurgical and the material properties like the microstructure, the grain size, and the more, and bring it into the model with FEM. Okay, after explaining about the FEM, why we use FEM and what is FEM, now let's talk about the history, the background of FEM. I can say that the FEM was developed almost 100 years ago, and the mathematicians gave such an idea, but the idea was just on the mathematical side. It means that it was just theory. But in 50s, for the first time, civil engineers started to use such a theoretical background, which was developed by mathematicians, to solve their problem. And the example of actually they used FEM for the first time in 50s for designing the structure of a skyscraper. So what they did, for skyscraper, you have a big structure, and so you have many beams in the structure. So calculating such a doing such a calculation for the structure was not easy. So they tried to use the FEM concept and FEM idea to solve the problem in the way that they assume each beam as one element. And that was a static problem, because we know that when you are designing a structure or a building, it's a static problem. And of course, just in the field of elastic deformation. So the problem was so simple. I can say the problem was so simplified. It was not so simple, but it was very simplified, just static, and considering each beam as one element. Okay, we have a question here. No, mathematically no, because when we say FEM, it's a mathematical model. So is there any better or accurate alternative better than FEM? I think you mean that? No. At this moment, we do not have. Actually, the inaccuracy and the approximation, you will understand later, it's hidden in the way we solve the equations. Because later we will explain that computer, computer cannot calculate the integral, so how it can calculate the integral, how we convert the equations, how we obtain the weak form, and these mathematical steps, some of them brings some inaccuracy, but it's really acceptable compared to analytical. And up to this moment, for now, we do not have a better alternative to FEM. Okay, we have finite difference method, we have finite volume, but the idea is more or less same, but each of them is appropriate for one category of processes or physical phenomena. Okay, where was I? Okay, I was telling that so they made it simplified in the form, and then still they had many equations to solve. So you can, I think it's at this moment it's unbelievable, but they started to solve the equations manually. A big team, I don't know how many people, started to solve the equation manually, and then they gathered the results, and then based on the result, they designed that skyscraper, because at that time they had no computer. But here in the 60s, the computer were invented, and a computer, then we can solve more equations more rapid. So when the computer invented, the improvement in the growth in FEM becomes faster and faster. In 1956, the first application of the FEM in the mechanical engineering, or I can say in fluid dynamics, was the calculation of pointed wings with Boeing in aerospace industry. And then end of 60s, calculation of Munich Olympia Stadium. And then in 70s, non-linear problem are taken into according. Then in 70s, when the computer becomes stronger and stronger, and the calculation capacity increased, then the scientists and researchers started to apply the non-linearity in the models, because when you apply the non-linearity, your calculation becomes, of course, more complicated. But when you have a strong computer, at that time it was not strong, but it was improving. So they started to solve the problem considering the non-linearity. And since 80s, the application of FEM is distributed in different branches like fluid dynamics, fluid mechanics, thermodynamics, electrical engineering, and geology, and many different branches of science. Okay. Short, I hope should go back. And okay, as I said, the application of FEM is not restricted to metal forming. Okay, we will talk here more about the metal forming, but it's very diverse. As I said, in static, like the designing such a building, in dynamics, fluid mechanics, which is called like CFD, temperature problem, acoustic, crash behavior, and fracture mechanics, and many different applications. Yeah, you can see on this figure here, it's almost, I don't know, maybe more than 100. It's just on metal forming, but you can see that how FEM can help in metal forming and forging. I was working, for my PhD, I was studying in South Korea, and I was working with a software company, and they were developing they have developed a metal forming simulator, and many companies in Korea and other countries were using their software, and these are some examples of using the metal forming simulator in industry. So you can see that many parts were simulated designs, and many design processes were improved using the finite element. Okay, and what's the purpose of using finite elements? What do we expect when we use the simulation or finite element method for simulation? Okay, we expect to calculate the process parameters and to calculate the characteristics of workpiece. You can predict before you produce, and you can predict the loads, and you can optimize the working tools. And in the case of economic side, you can minimize the time of development, the cost of development, and you can minimize the waste. And you can see you can optimize the process, and to quality, you can increase the quality. This is a very important topic these days. And what you need for doing this FEM or simulation, of course, the knowledge for the theory of FEM, not too deep, of course, because as a user, okay, maybe today I will talk a little bit about the equations, how it's solved, but as a user, you will never enter to such a topics. Okay, if you want to become specialist in the form of FEM, if you want to develop your software in future, yes, of course you need to know about these equations. But as a user, of course, no. Just you see the interface of the software, as you will practice it later. We will practice it later in our sessions, and then you should be able to set a correct simulation to obtain the result and to analyze the result. Because, okay, obtaining a result is one thing, but as an engineer, you should be able to analyze the result and conclude something correct. And of course, you need a suitable software and suitable hardware also, because a good computer helps to reduce the time. And of course, simulation needs time. Okay, it's not that like that, okay, I run the simulation and then this is the result. No, sometimes in industry, they expect such a things. And all the time I say that, okay, I can run a simulation in 15 minutes for you, but the result is not usable because it's just graphical. Okay, it's really beautiful, full of colors, and you can see that the process is inside, but the results are not useful, because first you should think about your model, how to model it, how to simplify it, in a way that it does not harm the result in your area. And then run the simulation, and then you should calibrate it with the experiment, and then you can obtain. So of course, simulation by itself saves the time. Okay, imagine that you want to design a die. If you want to repeat it in practice, okay, you design the die, and then, okay, it's not okay, then some analytical analysis on that, okay, and then change it in that way. Okay, making the second die takes, I don't know, 2-3 weeks, and of course it costs too much because the making a die is not cheap, and then again it's not perfect, and maybe it takes 1-2 years, but this process with simulation can take 1 month. So still 1 month is 1 month, but it's much more less than 1-2 years with that huge amount of time and money you should put. Okay, so you can see an example here by Hyundai Motors here. They use the simulator for the metal forming and the process and the die design, and they could save $63,000 per year. Instead of try and error, and they use the simulator, and they could have such a saving. Or here in the from the quality point of view, as I said, it's very important to increase the quality. This on the left side, it's predicting the risk of damage on the cross section of a flange. So you can see here is a high risk area, and exactly in the experiment you can see that the crack is appeared here. So when you have such a simulation which can predict this defect, then on the next step you can start playing with the parameters and like the die design and temperature and the material properties and whatever to remove such a problem. Okay, these are 2 other examples of how simulation and FEM can help. This is the metal flow lines in a specimen. So in the first design, the weight of a specimen is 1.1 kilogram, and then by simulation and checking the metal flow lines, they could conclude that they can remove this part and it does not harm the quality. And then again they made it smaller, and from 1.1 kilogram it's just 800 grams almost. And it's a big save, because it seems that it's just 300 grams, but it's a mass production. On the forging, it's a mass production, 1,000 per day, 1,000 workpiece per day, or more or less. So it's a big saving in material. And here also, improving the design by using the finite element methods. Okay, I talked about the industry, and here I give some example I have used for the simulation at IMF in our Institute of Metal Forming. So this is an example of melt flow in a twin roll casting process. In this process, the liquid metal, it's magnesium or sometimes steel, it comes between the rollers and then solidified and rolled at the same time. So we simulated the process and we solved different problems. For example, in this plate here, we had a problem of distortion. It was distorted during the process. So by simulation, we found that the temperature in some parts reaches to even more than 1,100, and some phase transformation happens. That phase transformation leads to volume change and cause such problem, and then we could change the material and we solved it. In this case, this is the velocity field of the melt in the tan dish here. So then we had some segregation on this line, and then we could find the source of segregation. What is the source of segregation? And then we removed some of these struts, and we solved the problem. In this case, is predicting the solidification. As you can see, the solidification fraction. This is the twin roll casting of wire. It means that the melts come from one side and the wire comes out from the other side. And again, we could predict the solidification field, and still this research is going on. This is another example of optimizing the die in another project named Hip Crash. So you can see that we could run the simulation with the different die design at the corners, and then you can see the corners are changing, and then we compared, and with the damage criteria, we decided about the design which does not harm the soundness of the workpiece. And then this plate was from magnesium. Then it should goes in another process, becomes a composite with the polymer and the aluminum or magnesium in the layered composite. Then we simulated all together how it deforms and how it behaves and how the polymer escapes from between the metal plies. Okay. So many examples, many practical cases. So I said that finite element is really good compared to analytical approach, but still some errors comes into the calculation. So how the error comes? This is the process we have in the finite element method. This is the physical system or the reality. Then we try to find a mathematical model for that. So it's a kind of idealization. Okay, when we idealize it, then it means that we simplify in some manner, because as I said, we cannot model it without simplification. So a part of error comes from here at the beginning, but it depends on the skill of the engineers and the person who is simulating that make it minimum. And of course, if you bring everything, then or many things in your simulation, your simulation is big, it takes too much time, but you should find the balance between sacrificing this aspect and just saving the time. Okay, then we have discretization. We will talk about it, and we will talk about the equation later. So it's okay, imagine that this is your sample. In reality, it's composed of many particles, millions particles, But in finite element method, as I said, we should break it down to small pieces, we call it mesh or meshing or elements. These are elements, and you have nodes here at the corner. So some errors comes from here to here in discretization. And some errors come to into the calculation when we solve the equations. It depends on the method you are solving, but okay, for example, usually we convert the equations from the differential form into the integration form, and computer, when wants to integrate, you should give some numerical way, because the computer cannot solve the integrals in the way we solve in so some numerical methods for solving the integrals, and it brings some errors again. So we have error in simulation and discretization, and total in our process we have error in simulation, discretization, and modeling. But still, it's not too big compared to analytical approach, because analytical approach is far from reality. Usually we cannot make it even near or similar to the reality. So, okay, still this slide is talking about what I have told in the last slide. And yeah, of course, okay, I can here I can say that this is your meshing system and your elements. And if you start, to increase the number of elements or to decrease the size of the elements and the mesh, imagine that this is the reality. So your answer, of course, converges to the reality. It improves more and more, and it becomes more similar to the reality by increasing the number of mesh. But you should remember that increasing the number of mesh means that increasing the time of calculation. Sometimes it becomes so big that you need very supercomputers to solve it. So you should see what tools you have in the for your hardware, and then decide about it. Usually the things you should do that you should study this. Usually in any simulation, you should study the effect of mesh size on your results. It means that you start from a rough mesh first, and then starts to increase the number of elements. And after, I can say at a critical value, and after that, the dependency of the result to the mesh size becomes very, very, very low. Of course, if you increase the mesh numbers more and more, the result improves, but that improvement is not too much. It's not too much, so you can find that critical value for the mesh, and then you can continue your study with that critical value. Okay. So here we have a glance on the structure of metal forming simulators. Okay, as a user for the metal forming simulator, first you should computerize your design in CAD software, and you should give it you can use the different type of file to give it to preprocessor your design, and then you should give some other input data about the material properties and so on, the friction, boundary condition, which includes the friction and thermal condition, everything, and then it goes to the finite element solver here. So what goes on in finite element solvers, you can see in this box, very abstract. Okay, basically we have three law of conservation, law of mass conservation, Newton's law of motion, and law of energy conservation for the thermal part, for the mechanical part, and for the deformation. You know that we should keep to the law of stick to the law of mass conservation. And this fulfilling these equations is very important, and it affects the influence on the accuracy of your calculation and your simulations. So it comes to some governing equations. For example, law of mass conservation. Then it's stated in the form of equation of continuity, then equation of equilibrium, and the equation of heat conduction. 3 types of equation we have. Excuse me. And which these 2 are interconnected in this way. And then on the next step, when you have the equations, then you have treat the equations in the way that the computer can solve it. Then finite element equations are generated. We explain it more later. And then finally, you should obtain the results and send it to post-processor, and post-processor can make graphs and can prepare the result for you. And it depends on that what parameter you want to investigate, or you want to simulate or predict. And sometimes, you can couple the metallurgical phenomena here, as I said before, for FEM. So this is the main structure. Any question up to here? If I'm going a little bit fast, because we have many things to say in these 2 sessions, unfortunately, hopefully it's being recorded and I can upload it later. Okay, thank you for now. I could understand that I'm on the air, and okay, you can hear me. So, and what are those basic equations? I talked about it in last slide. As I said, we have equilibrium equations. It's more or less familiar for you because it's fundamental of metal forming. We had such equations. And also, because in deformation, the particles moves, then you have kinematic also. It means that you should be able to calculate the strain using the displacement field, using these equations. And very important things is that you should be able to connect the stress and strains to each other. Yes, okay, you know well that in elastic deformation, we have the Hooke's law. So that's Hooke's law states that it's a linear relation between the stress and strain in elastic region. And for the plastic region, we have von Mises-Tresca criteria to detect that the plastic deformation is started or not. And we have some equations, other equations for calculating the plastic deformation. Okay, and then boundary condition, we talked about it. And here you can see that what's the concept of boundary condition. For example, in such a problem, you have heat convection, heat radiation, heat transfer to the dies, contact with the dies, so you have friction here. And so all of these are applied to the mathematical form as a boundary condition. Of course, you know that if you want to solve a differential equation, you should have some boundary condition in the mathematical point of view. Yeah, same. Because we are solving those differential equations. Finally, I mean, our calculation is based on those differential equations. So of course, we need some boundary condition to solve the problem. And these are the boundary conditions, and of course these boundary conditions are the source of non-linearity, as I said before, because for example when you have the large deformation, then there is no linear relation between the stress and strain here, but okay, we can assume that in elastic it is, but in plastic it's not at all. And the same for contact, for radiation, all these things, and even the material properties brings the non-linearities or inlinearities into the problem. So these are the structure of the base equations, and if we want to go deeper, then we have the governing equations for the mass conservation, which is important, very important in metal forming. Then this is the equation, this is the differential form of the equation. Then you can see that what is, for example, this is the rate of density, and then the gradient of the velocity, and it should be equal to 0. And also for momentum, this is the equation we have, and same for the thermal part. This is the energy equilibrium equation, and yeah, the gradient of the heat and so on. Then you can see what are the basic equation are used in metal forming. I can say, okay, it's better to focus on metal forming from now on in metal forming simulations. And of course, you have some initial value. You need some initial value, initial temperature, initial geometry, and so on. Okay, and these initial values are given by this equation to solve the problem. And as I said, you have the boundary conditions for the heat transfer, for on the mechanical side, for the force on the boundary. So you can see that these boundary conditions are defined on the surface. These are the surface, but the other parameters you calculate is in the volume of the material, because so what we have to do is, okay, we want to solve some differential equation, but we cannot solve it in that way with computer. Then we should obtain the weak form of the equations. What is the weak form? It's a form, I can say that it's integral form of those equations. Okay, this is, for example, this is the momentum equation, as you can see here. Then we multiply it with this WU function, which we call it the weighting function. And then, so you can see these three terms, this, and they are here, here, here. And then we calculate the integral on the whole domain. On your workpiece, whole domain. And then this last term is the boundary condition. So using the weak form, obtaining the weak form, the boundary conditions brings into the calculation as a term here in the integral form again. Okay, this is the weak form of energy equations, this one. Then you can, again, comparing these two, you can understand. And this, and then after obtaining, so initially we have the differential equations, then we obtain the weak form of the equations, which is the integral form, and that is more appropriate for computers to calculate it, of course, by using some numerical methods. And then after that, we should apply it on the elements. I mean, we should solve the equations for each element. So what we have to do in finite elements, and then when you solve those equations on an element, then you have the value just on the nodes. The nodes, okay, nodes are here. Okay, for example, this element this is the 2D simulation, of course. For this element, you can see we have 4 nodes. Then when the computer solves, then you have the value on these 4 nodes also. But what's going on inside here? Then we use a kind of interpolation function. Again, I will explain about it more later. We use the interpolation functions to develop your calculations and to connect all the nodes and the result obtained on the nodes together and make it like obtain the answer and the results for all over your body, your workpiece. So, and this is the definition of obtaining the weak form, as I said. If you want to go deeper, this is a very simple example of obtaining a weak form of this simple differential equation. It's the same, so we have to multiply the equation by a weighting function, and then using this equation, which is familiar for you, you can reduce the order of the differentiation and make the equation simple and obtain the weak form of simulation in this way. This simple example can help you to understand, and I recommend you to try to understand it and try to obtain. Maybe you can find some other examples in internet to understand how you can obtain the weak point of a simple equation. Of course, as I said, as a user, if you want to use, you never go on this side, on the mathematical side, but it's good to know that what's going on inside. Some of you maybe in future wants to become a developer or to become maybe develop such a simulator for your country, for example, instead of using the software from other countries. Okay, and then we have the discretized equation in this form, and the parameters are in the weak form, in integral form. So it seems that everything is ready, and the computer now can solve the problem. About the discretizing, we can do 2 types of discretizing. Okay, as I showed in previous slides, one type of discretizing is on geometry. So it means that you break down your workpiece into the small pieces. It's a kind of discretizing, right? But on the other side, you should do the discretizing for the time also. Okay, if your problem is static, like the design of that skyscraper, which is a static problem. So time is not important. You apply the load and then you calculate the deformation. It's not time dependent actually. In that case, no need to discretize your problem based on the time, according to the time. But in deformation, you know that we have to do it, because you have a process, time is going on, and your deformation is happening. So for example, later I will say that to calculate the deformation in plastic form, you need the strain rate. When you need the strain rate, it's dependent on the time, right? Because the definition is d epsilon dt. So you should, beside the discretizing the geometry and break it down into small elements, you should discretize the time. Okay, for example, your simulation total time is 5 seconds. Then you should discretize it into small pieces of time. For example, it depends on the accuracy of your simulation and how much how accurate you want the result to be. Then, for example, to 1 second or 0.1 second, and then you should repeat the calculation for all nodes at each time step or each time discrete. This is the concept of time discretization, and then, of course, you similar to what we have done for the weak form and the calculation for the time. Also, we should integrate using these equations and calculate. For time integration, the Newmark method can be used, and inside that you can use under this topic you have the forward integration and backward integration concept, which each methods to calculate to integrate or to calculate has its own advantages and disadvantages from the point of stability. Some of them, the mathematical stability is low, in some of them is better. So I do not go inside that too deep, but okay, generally this is the concept. So you should discretize the time in your problem, and then use the mathematical tools we have introduced to calculate. Okay. And okay, as I said, okay, in the case of method forming, you should be able to connect the stress and strain to each other. So, okay, in the case of elastic deformation at the beginning, okay, you know that we assume it linear, so it becomes much more simple here because, okay, it's a linear relation between the strain and stress. However, even for the elastic deformation, it's not linear exactly. Still, so you can find some non-linearity here, but okay, it's acceptable up to here. But after that, for the plastic deformation, clearly you can see that it's not linear. So, okay, for plastic area, we talked about this yield criteria for Tresca and for von Mises, and how we can plot it. And when you are inside this area, then it's elastic deformation. This oval one is the von Mises, as you know, and this hexagonal one is the okay, octagonal. One is the Tresca. So inside that it's elastic and outside it's plastic. But when it goes to the plastic, then you need some more equations. When you go into the plastic area, then, okay, in elastic area, we said that the stress, sigma equals to E epsilon, the Hooke's law. Stress and strain are linearly connected. But in the plastic deformation, strain rate is connected to the stress. So now you can understand that it's important. In metal forming simulator, it's important, time is important because you need the strain rates. It's a really important component here in your calculation. And okay, so this is the basic equation for calculating the plastic deformation. Beside the Hooke's law in elastic area, you can use this equation for plastic area or plastic domain. And okay, we talked about this discretization, and then I want to talk about the interpolation. As I said, okay, when you solve the, okay, anyway, using that, converting the equations and the discretization, and then you obtain the values on the node, or you obtain the nodal value. Nodal values here, here, here. But you know, in your simulation, you need the continuous result. So these nodes, okay, what is the value here, or what is the value here or here? So we use this mathematical idea. It's interesting mathematical idea for calculating the values in between using a function which is named the shape function here. It's defined like this: n1 t1 to n4 t4, because we have 4. It's a 2D simulation and we have 4 nodes here as an example. The value of the shape function is defined in this way in the calculations based on the R and S we have here. Okay, so for example here, okay, and imagine here at this node, at node number 4, the S value is 1, the R value is minus 1, okay? If you put S1 and then R minus 1, then it becomes what? Okay, it becomes 0, okay? And the same you can calculate, and then you will find that just the value on n4 is 1, and these all 3 becomes 0. So when you are here, the value is exactly the nodal value. So it should be n4 becomes 1, and then 0, 0, 0. So the value becomes n4 becomes this value. I mean the value on the node 4. Okay, right. And if you try, you can check it on node number 3, 2, and 1, and you will find the same result. But in between, if you give some value here, for example, just minus 0.5 for R and then 1 for S, then you can obtain the value here, which is a combination of these 2 values, these 4 values for these 4 nodes. I can say that it's a kind of interpolation, and it's a kind of bilinear interpolation in the case of this here in a 2D. So I can say it's a kind of making average, but it's not a simple average. It's a little bit complicated. So in this way, we can calculate the values in between using this shape function and this main function and these shape functions. And graphically, you can see how it behaves and how you can calculate. So even manually, you can obtain some values. Okay, if temperature here is 900, 100, 650 here, and then you can obtain the value for this point, for example, here, based on the coordination and these equations. Then you can understand that how the software and the calculation goes on to obtain the comprehensive result for the nodes and between the nodes. Okay. Finally, when you obtain the equations for I can say that for each node you will have some equations to solve, and then if you want to solve it for all over your sample, your problem, then it becomes like a matrix form. This matrix form, for each equation, for each node, you will have an element in matrix here. So as you can see, for example, here, this is the displacement vector, this is the load vector, and what is connecting these two is called stiffness matrix. Stiffness matrix. So if if you increase the number of the nodes, increase the number of elements, this stiffness matrix becomes bigger and bigger and bigger. Maybe it depends on 1000 in 1000, for example. So it's a very big, it's a huge amount of calculation that computer has to do, but fortunately, most of the time, many components, many components in that matrix are zero. Then it becomes a little bit easier. And okay, as I said, to solve we changed the differential equation into the integral form, and now for solving even for solving the integral form, I said that the computer needs a numerical method. Now it's an algebraic form of this integral. We converted somehow using this Gauss integration method. So then when it becomes in this form, then computer can solve it and can obtain the result for your problem. Okay. Okay, this is about the stiffness matrix, as I said. So you can see that just in this band in the middle, you have the value for the stiffness, and at the corners usually you do not have. This is the case for all this example, and this color shows that, for example, this node 1 is connected with node 2 and with node 4, but it's not connected with other nodes. So you can see that we have 1, 1, 2, 1, 1, 2, 2, 1. Okay, the color shows the connecting between the nodes. So for which of them, between which of them we have the stiffness matrix. And in a bigger scale, it becomes, for a bigger scale problem, it becomes like this. Then you have such a band here, and for these dark ones, you have to solve the equations and you have some value. But for the others, it's fortunately it's zero in many cases if you model it correctly. And then you can obtain the value for nodal values. And this is an overview on the topic, because I think we talked about, on the second half of the lecture, we talked about mathematics and different methods, but in your mind, it should become clear that, okay, well, what is the structure of using these tools, these mathematical tools? Okay, at the beginning, we have the finite element FEM here, then it becomes to the discretization of the domain, as I said, making the small elements, and under that, then you have the different type of element. We will talk about it in few slides later. Okay, so this is clear. The concept is for discretization of domain is clear. Of course, as I said, we have the discretization for the time in our problem. Then identification of interpolation function. We talked about the interpolation function and what's the usage of interpolation function. It's explained here. And then we have the derivation of the elemental stiffness matrix and load vectors. Just in the recent slides, we talked about it. And then we should assemble all these together and finally obtain the result. So this is the general structure of FEM. If you want to know what branches, what tools are used, and what's the application of each mathematical tools in FEM, because FEM is a complex of different mathematical methods and tools. So as I said, fortunately, as a user, just you have limited tools when you open a software. You're not dealing with those equations, but yeah, you have the preprocessor. It means that you have to give some data about the process at the beginning, and then what we talked about, these equations and mathematics is inside here. You do not deal with it, and even you cannot open it. It's a kind of black box for the software inside. You don't have you cannot reach these black box here. But anyway, you know that the information goes to the solver solves the problem, and the results come to the post processor here. Okay, if I want to show it in a graphical way, this is the thing, this is the steps you have to take. On the CAD system, you should design your dies and workpiece, and then using the preprocessor, you give the design into the software. Of course, you should give the material properties from the database of the software, or you should find it in your research or on the internet. Anyway, you should give in some software database is available, in some software is not available, in some software you should pay for that. Next week, I will talk about the price of this software, and just to it's better for you to have an estimation about the price of the software we use for simulation. So I will introduce, I think on the final part of the lecture next week, I will introduce few famous software in metal forming, and I will give the price approximately. And then, okay, this material database is available. If it's available, then okay, you can easily load the material properties, and then it goes to the solver and it solves the problem, and the result comes to the post processor, as you can see here. So then you can extract the result, analyze the result, and solve your problem. Just as I said, we need to discretize the workpiece, and depends on the geometry. We have three types of elements: 1D elements, 2D elements, two-dimensional elements, or three-dimensional elements. Of course, just for rod, you can use such an element, and for beams, you can use the 2D elements like quadrangle or triangle elements. And for the 3D case, the example of the 3D elements like the triangular or the pentaedron, pyramid, or hexaedron, it's used in sheet metal forming, or it's used when you have a bulk forming in volume, and you need a volume elements. Of course, when, for example, in the case of 2D, when it's like quadrangle, it's more stable, and this calculation is simple. But of course, it's not. If your geometry is complicated, you cannot, because you should break it down to small pieces, and this is the only form you have. Then you cannot. Sometimes, usually, when your geometry is complicated, you cannot use this one. Then you should use the triangle elements, which is more flexible. Again, here in the case of 3D, hexaedron elements are the best from the point of view of stability of calculation, but in many cases you cannot discretize, you cannot mesh. It's better, you cannot mesh your workpiece using this kind of elements. Then you should use other types, and the most flexible one is triangular pyramid, because by using this form you can mesh any geometry, any workpiece. And the last point is that unit is important when you start the simulation. This last slide is just on the practical side, but unit is important. The most important thing is that you should stick to one unit, okay?